All right, today we are unlocking one of the most powerful tools in all of math, trigonometry. Now, I know, it sounds complicated, but at its heart, it's a really simple way to measure just about anything, from the height of a building to the distance to a star, and you can do it all without ever leaving the ground. So, to see how it's done, let's kick things off with a classic challenge.
So picture this. You're standing right in front of this huge tower. Your job is simple. Find out exactly how tall it is. I mean, how would you even start? But here's the twist. You can't climb it. No way. And the only tools you've got are a tape measure for distances on the ground and some kind of device to find angles. Now it seems impossible, doesn't it? Well, that's exactly what we're about to solve.
Okay, so let's really look at this problem. How can we possibly measure something that big with tools this simple? Well, the first step is to stop seeing it as an impossible task and start seeing it as a puzzle. And believe it or not, the secret to measuring that giant tower is actually hiding in something you see all the time, a ladder leaning against a wall. Yeah, that simple image holds the entire key to trigonometry. This is where we get to the core idea. The ladder's secret is all about the simple, totally predictable relationship between its angle and its sides. Here's the big takeaway. If you know how steep that ladder is, and that's just the angle it makes with the ground, and you know just one other length, like say how far its base is from the wall, you can figure out everything else. The height it reaches up the wall, even the length of the ladder itself. That connection right there, that's the magic. Okay, so before we can use this magic, we have to learn the language. Every right-angled triangle, like the one our ladder makes, has 3 sides, and each one has a special name that all depends on where you're standing. First up, the easiest one to spot, the hypotenuse. It's always the longest side, and you can always find it directly across from that perfect 90-degree corner. Think of it as the anchor of the triangle. Its position never, ever changes. Next up is the opposite side. Now this one is pretty cool because its name depends entirely on your point of view. Whatever angle you choose to look from, the opposite is the side that's literally on the opposite side of the triangle from you. And that just leaves the adjacent side. Adjacent is just a fancy word for next to. It's the side that's touching your angle, but, and this is key, it's not the hypotenuse. Easiest way to think about it is this. Once you've found the hypotenuse and the opposite, the only one left over has to be the adjacent.
All right, we've got the names down. Now it's time for the master key, the secret code that links those angles to the sides. And it's a simple little phrase you're probably never going to forget.
Here it is. So, ka, toa. Just say it a few times. So, ka, toa. It sounds a little goofy, I know, but these 3 little syllables are about to give us the power to solve our tower puzzle and a whole lot more. So let's break down that code. SOH tells us that the sine of an angle is the opposite side divided by the hypotenuse. CAH means the cosine is the adjacent side divided by the hypotenuse. And finally, TOA tells us the tangent is the opposite side divided by the adjacent. These 3 ratios are the fundamental rules that run the show for all right triangles. So we've got the language, we've got the code. You know what that means? It is time to go back to our tower and finally solve that impossible problem. Let's put this stuff to work. Okay, mission briefing. Here's what we know. From our standing spot, the angle looking up to the top of the tower, that's called the angle of elevation, is exactly 45 degrees. We used our tape measure and we are exactly 10 meters away from the tower's base. Our goal? Find the tower's height. So what's our plan of attack? Step 1, we just sketch out the triangle. We've got the tower going up, the ground, and our line of sight. Easy enough. Step 2, we label what we know. Our angle is 45 degrees, the distance along the ground is 10 meters, and hey, that's the side adjacent to our angle. The height we want to find, that's the side opposite our angle. Okay, step 3, pick the right tool. We have the adjacent, we need the opposite. Let's look at our code. Soha, ka, toa. Toa connects opposite and adjacent. That's our guy, tangent. So for our final step, step 4, we just write the equation. The rule is tangent of the angle equals opposite over adjacent. So for us, that's tangent of 45 degrees equals the height divided by 10. Now, here's a fun fact. You can punch it into a calculator, but the tangent of 45 degrees is always exactly 1. So our little equation just becomes 1 equals height divided by 10. A little quick math and there it is. The tower is exactly 10 meters tall. The impossible just became possible, all thanks to a simple little ratio.
And this logic works both ways. We use the angle of elevation because we were looking up, but you could use the exact same math with something called the angle of depression if you were standing on top of that tower looking down at something. It's the same idea, just from a different perspective.
But you might be wondering, why does this work every single time? Is it magic? Nope, it's just pure, beautiful geometry. Let's take a quick peek under the hood to see why SOHCAHTOA is so incredibly reliable. The whole system is built on one simple, rock-solid truth. For any specific angle in a right triangle, the ratio of its sides will always be the same. It doesn't matter if the triangle is tiny or gigantic, a 30-degree angle will always have the exact same sine, cosine, and tangent values. Always. Think about it like a blueprint. You can have a tiny little triangle on a piece of paper or a massive one formed by a tower and the ground. As long as they share the same angles, they're basically the same shape, just scaled up or down. And because they're the same shape, the ratios between their sides are identical. It's that consistency that lets us make these amazing calculations. So there you have it. We took a problem that seemed totally impossible and we solved it with a simple 3-word code. You now have a mathematical superpower that lets you measure the world around you. So really, the only question left is, what are you going to measure first?
Hello and welcome. Today, we are diving deep into the fundamentals of trigonometry. We're going to unlock the powerful language that describes, well, pretty much everything, from the stars in the sky to the very screen you're watching this on. So what is this secret language of angles all about? Look, at its heart, trigonometry isn't just some scary chapter in a math book. Nope, it's a system, a really beautiful language that's designed to precisely describe how things turn and relate to each other in space. And what's the big goal of this language? It's actually surprisingly simple. Trigonometry is all about making a connection between the measurement of an angle and the lengths of a triangle's sides. Think of it like a bridge between turning and distance. Let's start with the absolute basics, an angle. Just think of it as a way to measure a turn, right? If you stand up and spin all the way around, that's a 360-degree turn. If you just turn around to face the opposite direction, that's a 180-degree turn. It's really as simple as that. Okay, so besides degrees, we also measure angles in something called radians, and this is a really cool concept. Imagine you've got a circle. If you take the length of its radius and just kind of curve it along the edge of the circle, the angle you make at the center is exactly 1 radian. It's a much more natural unit that becomes absolutely essential in higher-level math. Let's move on and see how this all builds up. We're going to get into measuring with triangles, using probably the most famous mnemonic in all of math, SOHCAHTOA. These right here are the absolute building blocks of trigonometry.
For any right-angled triangle, we have 3 main ratios. Sine, which is the SO part, is just the ratio of the side opposite the angle to the hypotenuse. Cosine, the ca, is the adjacent side over the hypotenuse, and tangent, or TOA, is the opposite side over the adjacent side. This little acronym is seriously your key to remembering everything.
Now for our 3 main functions, we also have their reciprocals. And all that means is you just flip the fractions upside down. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. You won't see them as often, but they're still part of the family. All right, now for my favorite part, the power of identities. I love to think of these as trigonometry's secret cheat codes. Seriously, they're rules that are always true, and they let us simplify and solve problems that would otherwise be an absolute nightmare. And this one right here, this is the cornerstone identity, the most important one of all. Sine squared theta plus cosine squared theta always equals 1, no matter what. It comes directly from the Pythagorean theorem, a squared plus b squared equals c squared, and it's the foundation for so many other relationships. But here's the best part. You don't even need to memorize the other 2 main identities. As long as you remember that first one, you can create the others yourself. Just divide the whole equation by cosine squared, and boom, you get the second identity. Or divide it all by sine squared to get the third. It's this beautiful interconnected system. So here's the crucial point. Identities are your toolkit. They're not just some random formulas you have to memorize for a test. They are the tools you're going to use to take a complicated mess of an expression and simplify it down, or to switch between functions to make a problem actually solvable. Okay, so we've got our tools, now what? Well, let's put them to work. In this next part, we're going to take everything we've learned so far and use it to solve the angle puzzle. Here is a systematic, four-step method that will always guide you to the right answer. First, you simplify the equation using those identities we just talked about. Second, you get it down to a basic form, like sine of theta equals some number. Third, you solve for the main angle. And fourth, and this is the step everybody forgets, you have to find all the possible solutions within the range you're given.
Let's try a classic example together. We need to find all the angles between 0 and 360 degrees where the sine of that angle is exactly 1/2.
So what's our thought process here? Well, the first answer that probably pops into your head is 30 degrees, right? Because the sine of 30 is 1/2. But we can't stop there. We have to ask ourselves, where else on the unit circle is the sine value positive? Well, sine is also positive in the second quadrant, so there has to be another solution hiding in there.
And there they are. Our first solution is that base angle, 30 degrees. The second one, the one hiding in the second quadrant, is 180 minus 30, which gives us 150 degrees. So two solutions, not just one. That's the key. So, we've gone through the rules, we've solved a puzzle, but why does any of this really matter? This is where we go from just looking at abstract rules to understanding them as truly powerful, useful tools.
Let's circle back for a second to degrees versus radians. Why did we even bother with radians? Well, degrees are simple counting units, and they're great for basic geometry. But radians? Radians are natural length-based units. If you're going to move on to something like calculus, radians become absolutely essential. The formulas just don't work as cleanly without them.
So, we've seen that trigonometry is a language for describing angles, a toolkit for simplifying problems, and a method for solving puzzles. It's a fundamental part of how we measure and make sense of the world. The only question left is, now that you have the tools, what puzzle are you going to solve?